So consider the following rational function. So remember, we have a polynomial divided by a polynomial, p of x divided by q of x. To integrate rational functions, follow the below general guidelines. So there's two steps. Step 1, you're going to classify the rational function as proper or improper. Okay, so you'll classify that as proper or improper. If the rational function is improper, perform long division to obtain s of x plus the remainder divided by q of x, where q of x is the denominator. This is what we have just done in the previous example. So we had some improper rational functions. We performed long division. You could see that in each case we could integrate s of x using the regular methods that we already learned. And then in all of the previous examples, r of x over q of x was a proper rational function, and we were able to integrate it. Okay. Now, in some cases, we may not be able to readily integrate it, where it can give us something of ln x, but we'll examine that case. So note that r of x divided by q of x is proper, and again, you integrate s of x as you normally would. So that's the case if we have something that is improper. Step 2, you need to fully factorize the denominator q of x. So coming back to this p of x, if p of x over q of x, if it is just proper, you get the question and it is just proper, you come to step 2. You cannot perform long division on it, right? However, if this was improper and you performed long division on it, you would have gone through step 1, then you would have obtained something such as r of x over q of x. And now, assuming that you can't just integrate that using the techniques that you already know and using this formula, okay, using that one and the substitution rule, then you'll come to step 2. And this is the q of x that I'm talking about in either case, okay, in either one of these cases. So you're going to fully factorize q of x of the proper rational function. Then you're going to express the proper rational function as a sum of partial fractions by classifying the denominator q of x according to the 4 cases. Now there are 4 cases for partial fractions, and I'm going to go through each case and you'll see how to actually perform partial fractions. Now, instead of giving you a list of notes and discussing what each case is, the best way for me to explain how to use partial fractions and do the method of partial fractions is to just dive straight into examples. And that's exactly what we're going to do. So remember, there are 4 cases to consider when you are using partial fractions. And case 1 is where the denominator q of x is a product of distinct linear factors, right? Remember what a linear factor is. A linear factor is something that just has the equation of a straight line, like 3x minus 7, minus 5x plus 2. That's a linear factor, right? And each linear factor, what does distinct mean? Each linear factor is only going to occur once in the denominator. In other words, in the denominator, you're only going to have 3x minus 7, and then you'll have minus 5x plus 2. So you're not going to have a situation, this is what distinct means, you're not going to have a situation where you have 3x minus 7 and then squared. Because when it's squared, in essence what it is it's 3x minus 7 multiplied by another 3x minus 7. Then it's not distinct, it's repeated. When it's distinct, it's only mentioned once. So distinct, you can think of only occurs once. All right. Okay, so let's take a look at example 7. All right, so take a look at what we have to integrate. So firstly, we need to identify that it is a rational function. It's a polynomial divided by another polynomial. The next thing to note, degree of the numerator is 1, degree of the denominator is 2, so 1 and 2. So 1 is less than 2, right? So it is a proper rational function. Now, can we just integrate this as is? Okay, can we basically use substitution to get it into a form where we have 1 over some variable, let's say or let's use u, 1 over u du, and that's going to give me natural logarithm of absolute value of u plus c. Can we possibly use u substitution here to get it into that form? Okay, no we can't, right? No we can't. We can't use u substitution to solve this. So we have to simplify this proper rational function. We have to get it into partial fractions. This is how we do it. So let's just ignore it's an integral for now. We are going to say 5x minus 4 over x squared minus x minus 2. The first thing to do is we need to factorize that denominator fully. So factorize x squared minus x minus 2. You will find that its factors are x plus 1 into x minus 2. Have we factorized it fully? Yes, we have. Great. Now, take a look at this. We have a linear factor. How many times does it occur? It only occurs once. Then we have another linear factor. How many times does it occur? It only occurs once. That's why this is case 1. Denominator q of x, there's the denominator, we factorized it. It is a product. See, it's this term here multiplied by that term there. That's why it's a product of distinct. Distinct, each one only occurs once. Linear factors. This is a linear factor, x plus 1, x minus 2, it's also a linear factor. That's why we have case 1. If we have case 1, this is what we need to do. Okay, so this is equal to, you're going to create a new variable, call it a over your first linear factor, x plus 1. Then you're going to have plus b over your second linear factor, x minus 2. There we go. All right, now what we need to do is solve for a and b. Now watch the next step carefully. What I'm going to do is I'm going to multiply. So what we have here is an equation. I am going to multiply this entire equation by x plus 1 into x minus 2. I'm going to multiply the left and right hand side by this term here. If I multiply this, right, by x plus 1 times x minus 2, can you see how the x plus 1 will cancel off and the x minus 2 will cancel off? So what I will actually be left with on the left hand side is 5x minus 4 equals 2. Okay, so that's what we're going to do. We always multiply by that denominator on the left hand side. Then what I did on the left, I have to repeat on the right. So I'm going to multiply a into x plus 1. In fact, let me write it out here so you can see it. A over x plus 1 multiplied by x plus 1 into x minus 2 over 1. You can write the 1 there, it doesn't matter. Can you see how the x plus 1 and the x plus 1 will cancel off? But the x minus 2 does not cancel off. So what I will have is a into x minus 2. Okay. Then what I need to do, I have one more term, so I'm going to take b over x minus 2, and I'm going to multiply it by x plus 1 times x minus 2. So the x minus 2 will cancel off, but the x plus 1 will remain. So it's going to be plus b into x plus 1. Now what I need to do is solve for a and b. And I solve for a and b by eliminating, so the variables here are x, a, and b. I'm going to eliminate the x from my equation. And how do I do that? I'm going to say let x equal to something, and I'll solve for a and b. And the best way to do that, the best way to solve for a and b, is to choose an x value such that you can get rid of an a and then solve for b, and then choose another x value such that you can get rid of b and then solve for a on its own. So don't just choose x is equal to 0, because if x is equal to 0, work with me, you'll have minus 4 is equal to 0 minus 2, that's minus 2a, and then you have 0 plus 1, that's plus b, and then this is an equation with two variables, so you'll still need to choose an x is equal to some other value, maybe x is equal to 1, and get another equation involving a and b, and then you'll have to solve those simultaneously. Well, you can't do it like that. It's a lot of work, and we don't want to do hard work, we want to do smart work. So this is what we're going to do. I'm going to say, let's be smart about this. I'm going to say let x equal to -1. Why -1? Because if x is equal to -1, that's -1 plus 1, that's 0. It'll be 0 times b. That will disappear. Then I'll just have an equation involving a. Watch how this works. So x is equal to -1. I'll say that. I'll say 5 times -1 minus 4. That's going to be -5 minus 4. That's -9 is equal to sub -1 in place of x. That's -1 minus 2, which is -3 minus 3a. This is where the clever part comes in. It's -1 plus 1, that's 0. 0 times b is 0. So I don't need to write anything out. Then I can solve for a. So a is equal to -9 divided by -3. That is, a is equal to +3. Then what do you think I should do to solve for b? So think about it. What should I let x equal to solve for b? So I'm going to say let x equal to +2 because that will make that term 0. So if x is equal to +2, then it will be, let's get this out of the way, it will be 5 times 2, 10, minus 4, that's 6, is equal to 2 minus 2 is 0. 0 times a is 0. I don't even bother writing that out. It'll be 2 plus 1, that's 3, and then it'll be 3 times b, so it's 3b. 6 is equal to 3b. This means solve for b. 6 divided by 3, b is equal to 2. Okay, so a is equal to 3, b is equal to 2. We have solved for that. We didn't need to do simultaneous equations. Let's fill that in. So a is 3, b is 2. So a is 3, b is 2. Now, that was partial fractions. That's how easy it is. Okay, that's for case 1. Let's get this all out of the way. And now we can integrate. So this here is actually this. And what I encourage you to do is get the common denominator, or not the common denominator, basically just add this up, get the common denominator, and check that you can actually get that term back. Okay, that's how partial fractions work. So what we have to do now is integrate 3 over x plus 1 plus 2 over x minus 2. And this looks familiar. This is what we did in prerequisite 1. Okay, we can use u substitution on that and that separately to integrate them and get something of the form ln absolute value of something. Okay, I'm going to do the shortcut method. This integral will be 3 into ln of absolute value x plus 1 plus 2 into absolute value of x minus 2 plus c. And that's how you integrate a rational function by using partial fractions under case 1. All right, exercise 8. So try this example on your own. All right, let's go for it. So we can see that we have a rational function, yes. I can also see that it's proper. Degree of the numerator is 1, degree of the denominator is 2. Can I integrate this using the normal methods that I know? Can I integrate it using u substitution perhaps? No, I can't. So I'm going to have to use by parts. The first thing to do is factorize that denominator. So we have x plus 5 over, factorizing that denominator, it's going to give me x minus 3 into x plus 1. Now, we always look at the denominator to classify it as one of the 4 cases. In this case, I have x minus 3, that's linear, it only occurs once. I also have x plus 1, it's linear and it only occurs once. That means this is case 1. So this is going to be equal to a over, write out your first linear factor at the bottom, x minus 3, plus b over x plus 1. There we go. Just a note, by the way, if you have, for example, let's say you had the x plus 1 and the x minus 3 first, and you had something like this. So you had a over x plus 1 plus b over x minus 3. That is, you change the order of your letters. Is that fine? Yes, it is. It's perfectly fine. It's just your working out is going to be a bit different. But at the end, regardless of whether you chose an a or a b for the x plus 1 factor, you will still get the same number. Right? So it doesn't matter what you chose as your letter, you will still get the same number here. Okay, so if you had an a here and I had a b here, but the actual answer is, let's say, 10, we will both get 10. So it doesn't matter what you label the variables. Okay, so let's go back to the way I had it. There we go. Now I'm going to multiply this entire equation by x minus 3 times by x plus 1. That will give me x plus 5 is equal to, and then x minus 3 times by x plus 1 multiplied by a over x minus 3. The x minus 3's cancel off, and I will get a into x plus 1. And then take this term and multiply it by b over x plus 1. The x plus 1's cancel off. I will get plus b into x minus 3. Great. Now, again, just don't go and choose x is equal to 0 because we always do that. Be smart about this. I'm going to choose x is equal to minus 1. X is equal to minus 1. The left-hand side will be minus 1 plus 5. That's 4. Is equal to, that becomes 0 because it's minus 1 plus 1, which is 0. 0 times a is 0. Okay, and then we will have minus 1 minus 3, that's minus 4. So 4 is equal to minus 4b. Let's solve for b. b is equal to minus 1. There we go. Now let's solve for a. So to solve for a, I'm going to say let x is equal to 3. So if x is equal to 3, watch what happens. 3 plus 5 is 8. 3 plus 1 is 4. 4 times a is 4a, plus 3 minus 3 is 0. 0 times b is 0. I don't have to write that out. So it's going to be 8 is equal to 4a. This means that a is equal to positive 2. So let's fill that in. So a is equal to positive 2 and b is equal to minus 1. There we go. That's how we handle this using partial fractions. Okay, now that we have that, what I essentially need to do is integrate. So this here is equal to that in terms of its sum of partial fractions. What I encourage you to do is add this out, get that common denominator, and simplify it into that form, just so you can see the connection. So now we're going to integrate 2 over x minus 3, and see we have plus minus 1 over x plus 1. I'm just going to write that as minus 1 over x plus 1. It's just simpler to see and simpler to integrate. If you don't want to write it like that, it's fine, as long as you get the same answer for integration. Now you can integrate these using u substitution, and again, that basic 1 over u du integral formula. So when you integrate this, you will get 2 ln absolute value x minus 3 minus ln absolute value x plus 1 plus c. And that's your answer.